Stokes Theorem. So let's recall the curl of a vector v was also the line integral of the vector on a closed loop that is surrounding a surface area S in the right-hand sense. And if I take a component of that curl, for example, Ez hat dot curl v, this can be written as the limit, the surface area, and the loop goes to 0. The path integral on a closed loop C dr dot product with the vector v divided by the surface area d sigma c. Okay, now we can also write this because the limit, this is in the limit s goes to 0. We can also write this as curl v, curl of the vector field v, dot product with the differential area vector d sigma z. So that's also taking the z component, or we can write it as dot product with d sigma for any component. This will be the limit as c goes to 0, closed path integral dr dot product with v. Okay, now we're going to consider two adjacent differential surfaces with a common border here. And we're going to do the path integral over the path C1 and C2. So this is going to have an area vector d sigma 1. This will have an area vector d sigma 2. Now applying what I have just written here for these two paths, we have curl of the vector v dot product with d sigma 1 plus curl of vector v dot product with d sigma 2 is actually the closed path integral for C1 plus C2 dr dot product with the vector v. Now, how does this work? Well, if you consider the closed path integral C1 here, we're going from top to bottom, but for this one, we're going from bottom to top along C2. So these two contributions along the boundaries will cancel out. So they're exactly the same, but in opposite directions. So we find that the line integral, the line integrals at the common boundaries will cancel out. So if we build a macroscopic area capital S out of d sigmas in this way, we're going to reach the conclusion the surface integral d sigma dot curl of vector v is equal to the closed path integral dr dot v. And this is for a macroscopic surface, because for all of such d sigmas, we see that the common boundaries for these will cancel out, and this can be written for a surface, macroscopic surface, which consists of a combination of d sigmas that are in neighbor. So this is called Stokes theorem. This is Stokes theorem. So curl of a vector field V integrated on a surface d sigma dot the curl is equal to the closed path integral dr dot V for the path that is basically enclosing that surface. All right. Now what happens if curl of V is equal to 0? So let's consider a line integral between points 1 and 2 consisting of path A and path B. And let's write the condition that the curl of V is 0. So we have the integral, closed path integral, dr dot product with vector V is equal to the path integral over the path A dr dot V minus the integral over the path B dr dot V. Because they're in the same direction here, we have to go along path A and along minus path B to reach the same point, and that, according to Stokes theorem, is equal to the surface integral curl V d sigma dot product with curl of the vector field B. Okay, so that because the curl of the vector field V is 0, this will imply the two path integrals, integral over the path A dr dot V must be equal to the path integral over the path B dr dot V. Okay, so that means this integral, the path integral, is independent of the path taken. The line integral of the vector field V is independent of the path taken. Now that sounds familiar from mechanics. So this implies that we can define a scalar potential, a scalar potential energy function, for example, in the case of force, phi as a function of space r, such that this vector field V can be written as minus the gradient of this potential phi. All right. Or we can write a small change in the potential d phi is equal to minus dr dot B. So they are equivalent. So if I go from point 1 to point 2 minus d phi, this is equal to, that's the integral dr dot V, remember. This is going to imply it's the value of phi evaluated at point 1 minus the value of the scalar evaluated at point 2. So that is to say, it only depends on the endpoints. So this integral depends only on the endpoints, which is independent of the path taken in between these 2 points. All right. So we can state the following result. If curl of a vector field V is 0, curl of a vector field V is 0, then the vector field V can be written as minus the gradient of a scalar function minus gradient of phi. So phi is a scalar potential. And in this case, the vector field V is then called a conservative field. All right. So this is an important conclusion. Now we have recalled the definition of the curl, one of the line integral definitions of the curl, which is the the curl of a vector field V, Z component is the limit as S and C go to 0, the closed path integral C dr dot V divided by the surface integral d sigma Z. Now this is going to be basically implying that we have a surface and we have a boundary of the surface on which we're performing the closed path integral. And if we write this in the differential form, we could also say that because we're taking the z component of curl V, we can just say this is curl V dot product with d sigma is equal to limit c goes to 0 closed path integral dr dot V. And if we consider two neighboring surfaces, with areas d sigma 1 and d sigma 2, the path integrals over path c1 and c2 will add up to give me a contribution which doesn't have anything from the boundary in between them, because this is going to have the path integral from top to bottom, but this will have from bottom to top, so they will cancel out. So I can say that curl V dot d sigma 1 plus d sigma 2 is the closed path integral c1 plus c2 dr dot V. And if I add up all such neighboring d sigmas, contributions from all such neighboring d sigmas, this implies that it's for a macroscopic area S, integral over the surface area d sigma dot curl V is the closed path integral dr dot V. This is Stokes theorem. And if curl V is equal to 0, we can see that going between 2 points, point 1 and point 2, the path integrals become independent of the path taken because of this curl V being 0 and using Stokes theorem. So that means the path integral is independent of the path taken. It only depends on the endpoints, which means we can define a scalar potential such that the vector field V is minus gradient of phi, or d phi is equal to minus dr dot V, and the path integral from point 1 to point 2 minus d phi is going to be phi minus phi 2 minus phi 1, which is phi 1 minus phi 2. So it only depends on the endpoints. So if curl of a vector field is 0, it can be written as minus the gradient of a scalar potential, and that vector field is called a conservative field.